Don't mind the noise of my cat having her dinner in the background. So what I have here, guys, is we set up an electronic speed controller and a brushless DC motor. Why did I do this? Because it's very, very similar to hybrid vehicles or electric vehicles inverter assembly, and this is our analogy for a permanent magnet synchronous AC three-phase motor. As you can see, we have the three phases here. I have a battery. This is again our analogy for our high voltage battery that would supply the DC power. The DC power is being chopped up. These are not IGBTs, but they are in fact MOSFETs, I believe, in order to give us the synthetic three phases, which are applied to the brushless DC motor. So you can see here, this is an outrunner DC motor, so the whole housing basically spins. And I think you can see the coils, as you can imagine. There's a three-phase stator in there, consisting of, I think it's 12 poles, I think, in there. I'm not sure. I'll disassemble this, and of course the permanent magnets are around the circumference of the housing here. So what I'm going to do is actually hook this. So I'm going to have the battery is then going to go to the inverter, speed controller in this case, and then the output is going to go to the brushless DC motor here again. So the idea is this is very, very similar in concept to what's actually going on in a hybrid vehicle, and maybe at a later date we can back drive this and see what we can get with respect to generation capacity. But I think you'll see on the video here, it does in fact have back EMF being generated. In fact, I'll point that out. So I'm just going to focus on the scope here, guys, the three-phase output, and then as you'll see, it's very busy on the screen. I will simplify it down to a single phase, and we'll see what we're actually looking at here. So let me get set. The little potentiometer is, I didn't point that out, but I have a potentiometer. The potentiometer input is going to be interpreted by the speed controller as a torque demand, speed control, speed command, let's call it. So I'm just going to start up. You'll hear the little motor operating in the background here, and you'll see this is going to be an extremely busy signal, and I will clean it up and we'll simplify it and see what we can actually see here. You'll hear the motor operating. So there's a little motor operating, right? So you can see the three phases there. The A, B, and C, doesn't matter. Colors are relative here. So you can see it's a busy signal, right? Just done at the very, very low end of the speed control on the potentiometer here. I'm going to speed it up. And I think you'll be able to see it gets progressively busier and busier and busier to the point of it gets a bit insane, right? So let me just chop the potentiometer down to nothing here, and we'll stop the drive. Let me do that again. Okay, that's what I wanted to catch. So I've got the trigger set up on the scope so that it cuts out. And it cuts out just at the right moment. You can see that once the drive is gone, right? Once the drive is gone, what we have left is just the back EMF signal, right? So as the motor winds down, what we have, of course, is a permanent magnet operating or rotating inside the coils, inducing a voltage. So that's the three phases that we have right there. And you can see it's extremely clean as opposed to the drive signal, which is filled with multiple spikes. So let me actually put on some filters, and it'll clean up the drive signal a wee bit, and we'll be able to understand the signal a wee bit better, because it's just chaos on the screen, right? Okay, so I've applied some filtration to all three channels, guys, here, all three phases here, guys. Let's see if we can get a wee bit better understanding of what's actually going on here. So that's a wee bit cleaner. We can have some idea what's going on. And I think with the filtration on here, you can actually see what we have on screen here is you can see the spikes. And I believe those are the spikes that are actually coming from the MOSFETs with respect to the drive. And you can see that what we are looking at here on all three phases is a composite signal. You can see the sine wave is there clearly. That is the back EMF, and on the back EMF is writing the spikes, which is the drive from the controller. I believe that's actually what we're looking at here, guys. Let me simplify this even further. We'll go to a single phase and we can see it in even cleaner detail. So I think you can see the signal in even a cleaner detail there. You can see the drive, which is basically the spikes, and you can see the back EMF given as the sine wave proper. Now this little brushless DC motor, the controller itself, actually utilizes the back EMF in order to synchronize it with respect to the timing on each phase. If it didn't look at the back EMF, it would have no clue how to time the rotation of the power that's being applied to each phase respectively. It's a sensorless brushless DC motor. There is no Hall effect sensor in this, so in order to realize the position of the rotor, it actually looks at the back EMF on initial startup and then knows how to time the signal respectively. So it utilizes the back feed as the actual feedback mechanism in order to keep track of where the rotor is. It's pretty clever. Let's look at the signal itself. We can notice that the frequency, the signal will actually narrow as the speed goes up, as well as the amplitude of the signal will go up. You'll notice we'll get more spikes on the screen, synonymous with the frequency going up. That's pretty close to maximum speed. And of course the frequency has gone up, right? So it's the frequency and the let me just move the trigger down a wee bit here. I think we can catch it in just the... Yeah, there's just the sine wave. So again, that's just the induction from the permanent magnets into the stator coil as it actually spills down. There is no drive coming from the board, and it's just the back feed, if you will. So yeah, I think we'll leave it at that for tonight, guys. I was gonna hook up the boost converter again, just to be more of a model with respect to hybrid vehicle or an electric vehicle. The battery, the boost converter going into the inverter, as I said, the speed controller. The speed controller essentially looking at the torque demand, the accelerator pedal, of course, in the car. Potentiometer is in fact a potentiometer in the car, essentially 2 or 3 channel. This is of course just a cheap potentiometer. And the drive, essentially the control board looking at what you want with respect to speed and power, and applying a control signal to the gate of the IGBTs, MOSFETs in this case, in order to provide as the chop of the DC at a certain voltage and frequency in order to generate the rotation that we require. There's a reverse switch as well, but who cares? That's kind of pointless to show that, right? So I hope that made some sense, guys, because it's making a bit more sense to me. Why did I buy this? Because I can kind of simulate, as I said, an electric vehicle at a fraction of the price, right? This was like 20 bucks, 30 bucks or something, and this was 20 bucks, you know, so if it blew up, which it did, or yeah, that was my reckless younger brother that blew the other one up. We can get an appreciation for what's going on. So I'm going to continue to model this as I become more and more familiar. I'd kind of like to see the gating signal on the board itself, if I can figure that out, again, without blowing it up while I scope it. If it does, it's not the end of the world, because that's the whole point to this model. So I hope that made some sense, guys. Again, we'll break this down, get a better idea with respect to regen, how that's handled. I was going to show that. Unfortunately, when I was back driving this with my drill, it's only generating like 1 volt peak to peak at the maximum speed of my drill, so I couldn't really forward bias a diode bridge in order to convert it to DC, which would go back to the battery, right? But I'm working on it. It's all coming. So I hope this makes some sense, guys. I hope it clarifies some detail. Again, the battery to the boost converter, not present, but I have it. We'll maybe install that in another video. To the inverter, speed control, applying the 3 phases, so converting the DC to a simulated 3-phase AC, which is applied. And of course, the whole thing is bidirectional. In reality, here, of course, it's only unidirectional. But I hope that made some sense, guys. It did for me. I liked it. I'm happy with it. I hope you got something out of it yourself. That's that, boys. Cheers.